I've swapped it. I've already been told off from and rightly so.
Good afternoon and welcome to the BAA Christmas Lecture 2019. Very many thanks for coming along and making this one of our most successful events, certainly capacity again. As new president, I'd like to sort of welcome you all. I would actually notice that you may on the, looking on the website, that it did actually come, apart from the president, my sort of, introductory bit came up as Alan Dowdle as president. So somebody pointed out. So I wasn't quite sure whether Alan wanted to take over now, but I thought I think the shortest running president has been a year, so I didn't want to ask just a few weeks. But anyway, can I initially express thanks to two people. There's a long list of thanks at the end, but I just wanted to express thanks to the IOP for letting us host the event here. Paul, thank you very much indeed. And also for somebody who, if in their absence, the event wouldn't take place, is Hazel Collette, the meeting secretary. So I'd like to just, if I can ask for a round of applause for Hazel, because she's put in so much work, as always, on this, and I appreciate that. So before we move on to the talks that one of the enjoyable parts of the president is to actually be able to present awards for people who've been notable in astronomy, and that first one is Robin Ledbetter, who was awarded the Merlin Medal. So if you'd like to, did you want to come up on? Presentation. Oh, I think I'm want to do that. And the Merlin Medal itself. Thanks so much, Eddie. Did you want to say a couple of words?
Yeah. I expect a lot of people know me as I'm the spectroscopist. How many star analyzer owners are there here?
Oh,
look at that! Fantastic. I hope you enjoyed it. You know, Elliot Merlin himself was a spectroscopist. He took spectra or used a spectroscope to view novae over 100 years ago now. But it was another medal holder, Maurice Gavin, who got me into this game. And of course, he was a pioneer of spectroscopy in the digital era, the electronic era with electronic cameras. And thanks to that technology, amazingly enough, we can still take spectra of those novae that Elliot Merlin viewed over 100 years ago, despite the fact that they're now over 100,000 times fainter. And I'm very honoured and privileged to be part of that history. And thank you very much for awarding me the Merlin Medal. Thank you.
Thank you very much. The next award is the Patrick Moore Award, Sir Patrick Moore Award, due to a generous donation to the BAA after Sir Patrick's death. The fund was created, or the award was created, for someone not necessarily within the BAA, but somebody in astronomy carrying on the ethos of astronomy and outreach to the general public, and for doing work to promote astronomy both with youngsters. And each year there is a small committee that's within the BAA who receive the nominations, and that then goes to council with their proposal or their suggestion, and then that's approved. I'm delighted to confirm that Dr. Stephen Barrett was the winner this year and has come along to collect with great pleasure. There's nothing I can do. It's a long way to.
Want a handshake again?
No. Thanks very much. Thank you. Okay, so from the next, this is more of an admin section. If I can just ask Jeremy to announce the papers that were confirmed at the council meeting this morning.
Yep, so this morning Council approved the publication of 2 papers in the journal. So the first one is Determining the Distances and Distribution of Young Star Clusters Using Gaia Data Release 2 Data. That's by William Sampson. And the second paper is Sunspot Numbers Without Active Region Numbers, and that's by Peter Meadows. Thank you.
Thanks so much, Jeremy. Okay, so next are speakers this afternoon. Now, Prof Mark Kidger has very kindly come over from Spain for this afternoon, or not just for this afternoon. If I just explain a little bit of background, that my local astronomy society is down in Basingstoke, and I've known Mark for a number of years now. Most notably, he's been coming over to give talks to the Astronomer magazine run by Guy Hurst, and he's attended several of their AGMs down in Basingstoke. And over the last 4 years that we've been arranging for Mark to come over to talk to our society, and we've flown him over, and we've tried to sort of split the cost with other societies if it worked out. For this year, with me becoming president, I sort of approached Mark back in April time, I think it was, to ask would he be prepared to come over, but not just to talk to Basingstoke, but to do the main BAA lecture, which is today. Oh, and by the way, if you're coming over, would you mind talking to Basingstoke as well? Oh, and would you mind if we arrange for Newbury to come in as well? So what we came up with, the idea is that yes, the BAA would pay for his flight over, but as part of, our outreach to the wider astronomical community, so that more people could enjoy Mark's excellent talks, that did 3 talks. And just to put the icing on the cake, as far as Mark was concerned, I said, oh, can the talks be different? Because some people may be coming to different ones, and so, oh yes, I'll agree to that as well. And then Northampton muscled in on it as well and said, oh, here you're coming over, so please can we have a talk? So Mark is doing 3 talks, and probably he's not quite sure what talk he's doing on the Monday to Northampton, but a busy weekend for him. So Mark has previously worked over in both Tenerife and La Palma on the observatories there. I'm working on the Isaac Newton in La Palma and Herschel. Since 2006, he's been working for ESA, notably on the Herschel project, and in 2018 moved over to PLATO, which is the search for Earth II, Earth-style planets, of which is the subject of his talk this afternoon. He writes monthly on comets and meteors for the Spanish astronomy magazine. He also contributes notes for the Astronomer magazine on the comets, and does a bit of enjoying his cricket or watching cricket. And I think it's just something that reminded me. Did you once write a book on the spin, the science behind the spin of a cricket ball?
Something like
Something like that. So I always remember that. So that came up as a cricket one. But so without further ado, if I can pass you over to Dr. Mark Kidger and give you a warm welcome.
Thank you, Alan.
Thank you.
Does this work? Good heavens, it works. Right. What Alan didn't point out is that he also arranges for interesting journeys. And this year he has excelled himself. Quite apart from the fact that I got the extra talk added on, I heard a couple of months ago that I needed to be at ESTEC in the Netherlands for an important PLATO meeting on Wednesday. No problem. Last flight from Madrid to Amsterdam Tuesday. Last flight back Wednesday. Catch the plane to Basingstoke Airport or whatever the equivalent is, on Thursday. He had it all sorted out. And then as I was leaving for the airport Tuesday evening, I got a message from BA. Your flight has been cancelled and you have been rebooked Wednesday evening. If there are any French air traffic controllers in the audience, would you please leave now? It turned out that there was one spare seat on one flight on Thursday, and they managed to get me onto it. That wasn't Alan, that was a very helpful guy from Iberia. And so I actually did manage to arrive, only to discover that Alan had arranged a train strike as well. You are in for an interesting year. Anyway, subject today, I'm going to talk about PLATO, and I'm going to talk about the search for Earth II. However, as we are not NASA, we are not going to hype this up. One of the things I would tell you is, please be very cautious of the weekly press release that says we have discovered a duplicate of planet Earth. It is not true. Very few of them, if any, look even remotely like Earth. So, where do we start? Well, let's start with this quote from our Director General, because he's got spies everywhere, so it's a good way to start. I want to keep my job next year. Does a second Earth exist in the universe? One of the most exciting questions in astrophysics today. And that's one of the reasons why searching for planets around other stars and searching for possibly habitable planets is one of the biggest priorities of the European Space Agency. And we've actually got 3 planet search missions launching. CHEOPS, which the latest I heard is it was going to launch on December 17th. PLATO, which will launch in 2026, and then Ariel in 2028. Oh, I'm not, sorry, I did not. Yes, sorry, I thought that had been set up. I wasn't looking behind me. Yeah, whereas our audiovisual expert, you know your computer. Oh, right. Wrong button. Duh. That's a good start. That's it. That is a good start. Right, now we pay homage to the Director General properly, and we can continue. So, there were many years of announcements. We found a planet, famously Barnard's star, Professor van der Kamp, various other stars, Epsilon Eridani, and others. none of which were actually confirmed. And after finally 30 years of searching, Michael Mayer, Didier Queloz finally found a planet, and it's around 51 Pegasi, magnitude 5.5 star. It's there. It's not actually difficult to find with the naked eye. But on the image, you know, you can't see the planet. It looks just like any other star. But the planet was a bit singular. It was the first of what we call the hot Jupiters. So this was a very unexpected development. A star that's around about the size of the sun, the planet has an orbital period of 4.2 days and a surface temperature of 1,200 degrees centigrade. Not even NASA would claim that is Earth life. At least on a good day. It was a very disconcerting discovery, and it was a big challenge for the models of star formation. And it turns out of the first 300 exoplanets, planets around other stars that we discovered, about 80% were like this one, hot Jupiters. Jupiter-sized planets, very close into their stars. And there were also a few very large rocky planets, but nothing that looked remotely like our solar system. There was this one, 51 Cancri. This was the first one that started to look a bit like our solar system. There's a whole series of planets, multiple planets, one of which is around about the orbit of Venus, but with a quite eccentric orbit. 5 planets in total. They vary from about 8 Earth masses to 4 Jupiter masses. They're not exactly holiday spots, unless you mean like being crushed, and quite painfully, I would suspect. And it got to the stage where people were starting to wonder if our Earth was actually exceptional for some reason. This is one of the most extreme ones, WASP 121b, great holiday spot if you like sunbathing at 2,500 degrees centigrade in an atmosphere of boiling crust. The atmosphere contains lots of oxides of very refractory metals because the planet is literally boiling away. Now, I checked up the numbers before I left, and NASA lists 4,099 confirmed exoplanets as of, when was it? Sunday or Monday, I think it was, the second. And there are nearly 6,000 unconfirmed planets. Of those, less than 1,000 actually have confirmed mass. So unless you know the mass of a planet, as well as its orbit, you really don't know if it's even remotely like Earth. And if you go through the list, you'll discover that only 15 of these more than 4,000 planets are Earth-size or smaller. 107 of the planets with confirmed mass are at least 10 times the mass of Jupiter. That's where calling it as a planet is a bit of a stretch. You can call it a planet if you want, but it's more like a failed star. And the list is really dominated by those hot Jupiters. Why have we found so many? Well, it turns out there are around about 50 planet search programs in the world. Almost every observatory seems to have its planet search program. I think even Roger Dimmock's got a planet search program these days. You know, but they are mainly dependent on very high resolution spectroscopy. Now there's a challenge for the gentleman in the audience, our spectroscopist. Very high resolution on very large telescopes. It's very slow, it's demanding. And the easy way to do it is to look for stars with short period, big planets where the shift in the spectral lines, the Doppler shift from the gravitational perturbations of the planet are big. It's very difficult to have a lot of patience and look at a star over many years to detect a planet like Jupiter in our own solar system. To detect that, you would have to observe our sun for at least a dozen years and probably longer to be able to confirm it. There's a natural bias to looking for big planets close to their star, short periods. More distant planets, it's very difficult to find them normally. And the small planets, you can't even detect. But there is a alternative method for doing it. And this is the one that people are beginning to use with a lot of success now. But you've got to be very patient. Fortunately, astronomers can be very patient, sometimes. And that is to look at a big patch of sky and wait until a planet just happens to pass in front of the star. So like the transit of Mercury a few days ago, which I spectacularly failed to observe, third consecutive transit has been clouded out for me. Don't observe transits of Mercury with me, you'll never have any luck. Only about 2% of stars will actually show transits, but this is a very good way of looking for smaller planets. However, there's a problem. There are so many processes that can mimic a planetary transit. Star spots, stellar activity, stellar oscillations, the rotation of the star. There are various other effects, and only about 50% of all the transit candidates that have been detected over the years have ever been confirmed, because you confirm them with spectroscopy. So a lot of the Kepler planets have never been confirmed because they are the stars are too small, too distant, too faint to be observed with the technique from Earth. Now this is your ideal transit. There's your little planet. This would be about something like Earth or Venus transiting in front of the sun. You get a nice little dip in the light curve. That's the theory. Practice, though, of course, never quite so simple. This is a normal transit light curve. This is a very big transit. This is planet comparable in size with Neptune. Now, you've got to imagine that you're like Jocelyn Bell Burnell, who had 3 or 4 miles of paper trace, and she was looking for the little pulses in that. Because that light curve, instead of being just a little section that fits on the screen, it would go all the way up to Northampton and probably most of the way to Bristol, the other side. And you'd be looking for that little noisy dip in the middle, which is actually the planet. That's the trick in looking for transits. It looks easy. There's not a lot easy about it. However, NASA's Kepler satellite refined the techniques for doing this very nicely. It's a 1.4 meter telescope. It was put in an Earth trailing orbit, so it just very slowly moves away from Earth. It's about 0.1 AU per year. It's moving away. And it has a camera that is 95 megapixels. That's a decent size camera. Bit better than my mobile phone anyway. And it takes constant exposures of a field of view in northern Cygnus. Here's its field of view. Not quite overlapping fields. You see Deneb Alvario there. And it just looks at every star in that field of view, looking to see when one of them winks slightly. That's where the patience comes in. So here's the field of view a little bit larger. It's 12 degrees across, and it's observing 150,000 stars simultaneously, which is pretty good. There's plenty of data there. It takes photometry to a precision of 0.02, not magnitudes, millimagnitudes. That's 20 millionths of a magnitude, which is pretty good. So it's just looking for stars with periodic dips in brightness. And there are a lot of other missions that are going to follow on from Kepler. TESS is the classic. This is TESS launching. It's a mission that's looking mainly at red dwarf stars. So when they tell you that they found a duplicate of Earth, just remember that most red dwarf stars are flare stars. So any planets around them are going to be bathed frequently with hard X-ray radiation. If you like hard X-ray radiation, it's a perfect holiday spot. I'm not so keen on it myself, but no. So TESS launched April 18th, 2018, and started looking and has already found a few dozen planets. Now this is one of its commissioning images. Now I'm sure you all recognize this constellation. If I say that's the coal sack up there, this is the coal sack, that's actually the constellation of Crux. Gives you an idea of the sort of data reduction problem the TESS scientists have, because there's an awful lot of stars in that field of view. They're looking only for small rocky planets close into red dwarf stars. And it turns out that now, after Kepler, each mission has a very specialist target. So CHEOPS, which is just about to launch, is going to look at the planets that have already been discovered and try and measure their diameters much more accurately. Because if you measure the mass and you measure the diameter, you can measure the density, you know what the composition is. PLATO, which is my mission, or mission where I play a very small part like this, that will look for planets around sun-like stars. That's its priority. We'll also look at atmospheres around exoplanets. Now, earlier I met a gentleman upstairs at the registration desk, said, my friends bid for the design of PLATO. I think they supplied us with a Toblerone, and Astrium supplied us with a cash register, and apparently ESA decided that the cash register design was the better one. So the one on the left, this one here, our cash register, that's the one we're using. This is one of the PLATO telescopes, which are being built at the moment. So we signed the contract for it in October 2018. PLATO's had a bit of a rocky ride. It has almost been cancelled twice, and could still be cancelled in the middle of 2021. So if you meet me signing on at the job centre sometime in July 2021, you know what's happened. Not good news. And also our design has kept changing a little bit. We started with 32 cameras, then we had 28. Now we've got 26 to cut down on weight. Then we started with this design last year, and then the clever people who are building this thing discovered that we didn't have enough power, so we had to fit it with wings. So we've got extra solar panels that have been fitted to it. This should be more or less the final design. But it does actually mean that the PLATO mission logo has now changed 3 times. Well, changed twice. It's 3 different logos. Now, here's PLATO at a glance. We're going to launch on an Ariane 6.2. Now, if you get this question in Trivial Pursuit, what is the difference between a 6.2, an Ariane 6.2 and an Ariane 6.4? And the answer is, it's the cluster of booster rockets at the bottom. The 6.4, the more powerful one, has 4, and the 6.2 has only 2. You know, it's brilliant. The engineers have been really imaginative there. Now, we have a launch date. Emma's laughing because I think she's read this. December the 12th, 2026. But we have several days possible slip scheduled into the schedule. We could launch as late as December 16th. Do not believe this. No space mission that has ever been built has ever launched on time or ever launched remotely on time. Our betting is that even though we're right on schedule at the moment, something will happen. We have no idea what. We'll slip into 2027, quite possibly 2028. However, we will try and make that December 12th launch date. Put it in your diaries. So I said 26 cameras, and the accuracy that we're demanding of our cameras, which are all individual telescopes, is for a magnitude 11 star integrating an hour, we want 50 micromagnitudes. So that's 4 zeros and then a 5. Not bad. Right, so what are we going to be doing with these cameras? Well, we're going to be applying the Goldilocks test. You all know Goldilocks. She's an expert in porridge. The Goldilocks zone is the zone around a star where it's not too hot nor too cold for liquid water to exist, just like the porridge that Goldilocks was testing. Now, TESS, because they're looking at red dwarfs and they've got very small habitable zones around them, they reckon they might find, if they're lucky, 2 or 3 planets in their habitable zone. PLATO, by looking at much larger stars with a much bigger habitable zone, we are hoping that we will have 100 plus, maybe many hundreds of planets that pass the Goldilocks test. However, there is a warning. Not all porridge is actually as good as Goldilocks said. So we'll leave that for a bit later. So TESS and PLATO look as if they're actually doing very similar things, but they're actually doing it, they're subtly different, and they're doing it in a completely different way. TESS is observing 85% of the sky. 2-year primary mission, they've already got an extension, and they were hoping to find about 2,000 planets, short period planets. PLATO will look for at least 4 years. Theoretically, we can look for 8.5. If everything works, nothing breaks. So we hope to find a minimum of 4,000 planets in 4 years, so about 1,000 a year. So far, TESS is doing pretty well. It's got 34 confirmed planets, and it's got well over 2,000 candidates that are unconfirmed. So if we can match that, we're doing pretty well. And this is just a comparison. No, on the left-hand side, in the blue corner, the NASA champion, and on the right-hand side, the ESA champion. TESS's field of view is 2,300 square degrees, which is impressive. PLATO's is only 1,000 square degrees. We've got 2 fields, one in the northern hemisphere, one in the southern hemisphere. Our plan A is we will just stare at one of those fields for 2 years, switch to the other field and stare at that for another 2 years. And we're looking at about 265,000 stars in that time. So this is the design. Now the 26 cameras are split up. There are 24 normal cameras for faint stars. For us, faint star is anything fainter than magnitude 8. And we've got a couple of special cameras. So we have a field of view that is 47 degrees across. That's the field of view of our telescope. It's quite impressive. I was thinking 40, nobody's impressed. I thought telescope with a 47 degree field is pretty impressive. And then Within it, different areas will be observed by a different number of cameras. The cameras are slightly offset from each other so that we cover the widest possible field. The central 22 degrees, all 24 cameras will observe. And then different areas around it will be covered by 18, 12, and in the outer part, 6 cameras. Every 3 months, we rotate the field of view because the Earth is going around the sun, so we have to rotate the cameras so that the solar panels keep pointing correctly at the sun. And that gives us a nice calibration of the cameras. It makes sure that what we're seeing is genuinely from the sky, not some intrinsic problem in the camera, some trending. And then we've also got 2 special fast cameras which will observe bright stars every 2.5 seconds. Those are the cameras here, these 2. 4 groups of 6 cameras there, and then the 2 fast cameras. The normal cameras will take an exposure every 25 seconds. Not bad at all. However, we only send back the data for our target stars. I'll explain the reason for that in a moment. These are our 2 fields of view. You can see how big they are. Now, it's going to be easier if I do it over here. The northern field starts in Ophiuchus, Bootes, Hercules, Lyra, about half of Cygnus, right up to Ursa Minor. It's a very, very large area of sky that we're observing. So plan A is that we will observe each of those fields for 2 years. There's a possibility that a couple of years before launch, the scientists will decide that the best thing to do is observe 1 field for 3 years. Then we can look at longer period planets. So, what's our observing strategy? Well, our cameras are 4,510 by 4,510 pixels, and there are 4 CCDs per camera. So that gives us, if you add them all up, 81 megapixels per camera. Multiply that by 24 cameras, well, actually 26. That's a heck of a lot of cameras. And 25-second exposures, we're taking a lot of data. Our diet is 436 gigabytes per day. That's what we can get down to the ground station. So what we have to do is go on a diet to keep ourselves down to only 436 gigabytes per day. So what we do is we just download a small area around each of our target stars. So this is what a Plato observation will look like. It will actually be a bit disappointing. It will typically be a 6 by 6 pixel square. The exact strategy is still being discussed. It might not be squares, it might be circles or polygons of some kind, but it will look something like this. Now we've got 5 prime star samples. Sample number 1 is 15,000 solar analogues, brighter than magnitude 11. These are our best stars. These are ones most like the sun. If you assume that 2% will have transits, divide 15,000 by 50, that gives you about 300 of those stars should have planets, transiting planets. And then we've got 2 other samples of sun-like stars, solar analogues that are either a bit brighter or a bit fainter, with a smaller number of stars. And then 2 other samples of much lower priority. And we are going to do some red dwarfs. The red dwarfs are there, we can't ignore them, so we'll do them as well, just to fill in. Now, the problem with bright stars is, of course, they saturate your CCD. This is a problem I think most of you have met sometime or other. And this is what the field of view will look like when we're observing a star that's around about magnitude 7. You will get an awful lot of charge leakage. Well, actually, it doesn't. That's not so much of a problem. We need to collect 1,000 million photons from each star. That's a nice small number, 1,000 million, for each star to reach our target photometric accuracy. So it turns out that actually these saturated stars, you can recover all the flux from them. It just needs a little bit of clever software to do it. However, the problem is that one saturated star takes up probably as many pixels as 100 or 1,000 normal stars, and that's our bandwidth. So you don't want to have too many stars that saturate massively. And one of the things that's been done with the CCDs is to design them so that they have the greatest possible capacity before they start to saturate. So we will observe the fainter stars, but this is what happens when you observe a faint star. Plato will observe some stars right down to magnitude 15, but the light curves for these faint stars, just like they were for Kepler, are going to be pretty noisy. Much larger errors. It's still possible to detect the planets, but it's a little bit trickier. Basically, our data reduction pipeline looks something like this. So you have a mishmash of numbers coming down from the satellite to the Cebreros tracking station near Madrid, 35-meter antenna. We have a wizard in Paris Observatory who's writing our software. He waves his magic wand a bit, and out comes the rabbit from the hat, which is our planets. That's the theory. My job is literally to keep the magician under control and make sure he's documenting what he's doing. He's a great guy, but I can't get him to document it properly. He's not an air traffic controller, though, so that's not a problem. We need a lot of clever software to do this, and there are a lot of people in many different European countries, some of them here in Britain at Warwick, who are working on this. So, here's our transit again. Now, the first problem is that when you look at a transit, you only measure the relative size of your star and your planet. But if you want to characterize the planet, know exactly what kind of planet it is, you've got to know its diameter, you've got to know its mass. That's not so easy. However, we have a very powerful, very useful ally that's already been mentioned in this meeting. That's Gaia. Gaia has revolutionized searching for planets, because what it is doing is it's measuring the positions, the distances, the brightness of the stars with incredible precision. It's giving us such good information on spectral types, distances, luminosities, that already the planets that are being discovered by TESS, they're getting a mass and a diameter for the planets from their measurements a factor of 3 better than they were expecting, just because the Gaia data is so good. And Gaia is going to keep on observing, and they're going to do even better. We're coming up to data release 3, data release 4. I don't know if there's a data release 5, but still, the data will only get better. So, this is what a typical light curve for one of our stars will look like. Now, you may or may not have a planetary transit in there. What you do certainly seem to have is a lot of noise. So you would think when you look at a light curve like that, that's more than 1,000 days of data, 3 years of data, which is about the sort of light curve we'll get, that 99.999% of that light curve is just utter junk. You throw it away. You're not interested. Actually, that's not quite true. We'll be using absolutely all the data on these stars because we will be looking at these little tiny variations to measure oscillations in the stars. These oscillations, same way the sun is oscillating, these are great for telling us about the star. We can get an enormous amount of information about the star, its internal structure, its age, its diameter, its surface gravity, from its oscillations, particularly when we combine all this information with the information from Gaia. A lot of that is genuine variations in the stars. So, when we combine all this data, the oscillations, the Gaia data, and our own light curves, we reckon that we can get 10% accuracy on the mass, about 1 to 2% accuracy on the star diameter, and even we can get, with Gaia, 10% accuracy on the ages of the stars. That's tremendous information because that tells you how evolved a planet is likely to be. If it's very young, a very old planet. If its star is a very old one that's about to come off the main sequence, or it's a very young star and the planets are recently formed. However, we can't do the observing without a lot of help. Now, here's another very impressive number. There is a huge ground-based consortium around PLATO collaborating to confirm these planets. You've got to confirm them spectroscopically, normally on an 8-meter telescope. Anybody in the audience with an 8-meter telescope, come up and have a chat with me afterwards. We've negotiated an agreement with the European Southern Observatory that they are going to give us, I believe it's 50 nights per year on 8-meter telescopes down at La Silla over the course of the mission. That's a huge amount of telescope time, and it is ridiculously insufficient for our needs. So, who are you going to call? It's not Ghostbusters. Now, some of you, Roger, come on, you will recognize these two evil characters, won't you? I mean the two on the left, not the two on the right. This is my friends Ramon and Montse. They live in a suburb of Barcelona. That's their 30-centimeter telescope. We call them Big Arnie and Terminator. And you can see there is actually a pretty good family resemblance there. Do not get Montse angry, Roger. Whatever you put in your Facebook page, don't get her angry. They started looking at exoplanets some years ago with their observatory. What they do is literally they raise the telescope up on a piston, poke it through a hole in the roof. That's their observatory system. And this is one of their light curves. It's a magnitude 10.5 star, and this is the transit of an exoplanet. It's a Jupiter-sized exoplanet, but they have been confirming exoplanets for years. They've done a lot of them. Here's another one. And you can see, even though the error bars on an individual observation are quite big, this transit, it's an amplitude 2/100th of a magnitude. They've detected it very, very easily indeed. We are arranging a huge amateur collaboration program in coordination with the PLATO satellite. It's being coordinated from Austria. I know the guy who's organizing it. We've been talking about it. He's new to amateur collaboration, and I've been telling him, look at these people, they're already doing it, so that he's got some ideas. Anybody in this room who's interested in collaborating with a big ESA mission, you've got a telescope around 20, 30 centimeters, you could be of enormous interest to this collaboration. One little incentive, we don't go in for corruption in this country, is that to encourage people to collaborate, there may be some free CCD cameras being handed out later. But I didn't say that. Actually, that's going to be one of the incentives that because they want very standard data, they will be giving people CCD cameras, standard cameras, to take observations in return for these people actually using the camera occasionally to confirm our planets. So if you're interested, keep your eyes open. However, I said, expect a lot of hype, particularly from a certain space agency the other side of the Atlantic, about planets that they will sell you as looking like this. Do not necessarily believe it. We know that actually the Goldilocks zone is rather narrower than we thought. Now, recent research says astronauts can work in gravity up to 3G. I'm not sure I'd want to do it myself, but you can live in 3G and more or less remain operational. If anybody wants to volunteer for the experiment, I'd be delighted to hear from them. Temperature, though, is more demanding. As we know, our Earth, there's a greenhouse effect, the Earth is warming, and there is a point at which the greenhouse effect will run away. Positive feedback goes out of control, you can't stop it. That's what happened to Venus. Now, Venus theoretically should have liquid water on its surface. If anybody's seen any liquid water on the surface of Venus recently, the reason is that if you go a little bit closer, a little bit further, either the greenhouse runs away or it just isn't good enough. You move the Earth 3% further from the sun, and we'd probably go into something like a permanent ice age. Move the Earth 3% closer, and you'd probably be tending towards Venus. So, actually, when people say they're talking about they've got planets in the habitable zone, a lot of them are probably more like Venus or more like Mars than they are like the Earth. Do not buy real estate from NASA. Care. So, I said, only 32 known exoplanets are less than 3 Earth masses. So anything bigger than that, you are not going to enjoy walking around on the surface too much. Of all the exoplanets we know, only 16 are actually in the zone where theoretically you could have liquid water. And of those, there are only 3 that are smaller than 3 Earth masses and in the habitable zone. 2 of them look like runaway Venuses, and 1 looks like an ice ball. None of them, in my view, my humble view, actually are very good candidates to be called an Earth analogue. So, my conclusion on this is that Goldilocks's testing was remarkably deficient, and we should go back and we should rewrite the fairy story. Her porridge control zone was far too broad. She was very tolerant of deviations of temperature. We can't estimate how many genuinely Earth-like planets there are out there. It may well be that of all the Earth-sized planets that we discover, only a tiny fraction are actually genuinely Earth-like, because they are really in the sweet spot to be neither too hot nor too cold. But if we don't look, we'll never find them. And of course, whether we find a planet that looks like Earth, or we discover that there aren't any planets that look like Earth. Earth is a freak. It's a mind-blowing discovery. It has huge philosophical implications. Everything at the moment is guesswork. We really don't know what the numbers are and what we're going to find. By the end of the PLATO mission, we should have a good idea just how many Earth-sized planets there are around stars like the Sun. A good idea. We may, though, discover that planets like our Earth are extremely rare in our galaxy. That would be a mind-boggling discovery as well. Disappointing, but mind-boggling. Whichever way the answer goes. So, thank you very much for listening.
Thanks so much, Dean.
I've already tripped over my shoelaces twice, so...
There's no need to hide. I'm sure the questions won't be this bad.
Right, well, I should stay on my knees before you, shouldn't I? You are the president. So.
Hey, thank you very much, Dean. So we've got a bit of time before tea. Can I ask, I think somebody...
Gentleman there was the first by about half a second.
I get how important it is to work out how many Earth-sized planets there are, but I don't get how we can then find out the masses of those planets, and surely without the mass we can't say that they're Earth analogues.
Okay, so we combine the information that we get. Plato only tells us the relative size between the planet and the star. Gaia, though, tells us the distance, the luminosity. That tells us how big that star is. So when we combine the Gaia information about the star with the Plato information about the planet, put all the numbers together, do a little bit of quite simple math, and out come the numbers. And you can tell if it's rocky, you can tell if it's icy, you can even tell quite possibly if it's got an iron core or it's a silicate planet. We are going to be that sensitive just by combining two completely different missions.
Thank you.
So, gentleman there.
Okay, you issued a challenge to amateur spectroscopists concerning measuring Doppler wobble of exoplanets. The current status is that amateurs are able to measure Doppler wobble with planets down to 20 meters a second on bright targets.
That's really impressive. That's good enough.
Yeah. Now, given that we're 8 years down the line, and amateur spectroscopic capability is advancing very rapidly, do you think there will be any targets of interest for amateurs in that area?
Could well be, because you've got to remember that stars from magnitude 8 to 11 are our prime targets, but we've also got the fast camera that will observe stars up to about magnitude 4. There will be some planets around very bright stars for you to have a look at. So, but we'll have candidates from about magnitude 4 down to magnitude 15. Take your pick. There'll be plenty for everybody. Well, that's the problem with Kepler, actually. Most of the stars that they've observed are so faint that even 8-meter telescopes aren't good enough for what they need.
Can I ask a quick follow-up question as well?
Of course.
Do you want to use the microphone?
Sorry.
Yeah. Not for me, it's for the recording, yes, apparently.
Kepler and TESS, they downloaded all the light curve information, and that's had a great spin-off in other areas. I'm involved in a couple of pro-am projects which are using combining spectroscopy with TESS data, and in the past Kepler data. I understand that you can't download everything, but is there a possibility for targets of opportunity where you could pick something?
Did you see the big grin? That means it's an easy question. There are two answers to your question. One is that every 3 months, when we turn the spacecraft round, we will take full frame images, the whole, quite possibly the full 47 degrees field. They'll be needed for calibration purposes. That will only be every 3 months. I can't tell you at the moment. We were discussing this in a meeting a few weeks ago, how often or how many of these pictures we need. But we'll certainly have those, so we'll have a long sequence of regular images of the full field of view that will be available for everybody. The second thing is that 8%, not of the time, of the telemetry. So basically 8% of the pixels that we download will be available for any astronomer in the world to request. So anything that's in our field of view, 47 degrees across, you should be able to find something that's of interest. You can request that that be observed. So we're expecting to be asked to follow supernovae, comets, asteroids, variable stars, absolutely any quasars, Seyfert galaxies, anything you can imagine. 8% of the bandwidth that we've got available, so just calculate 8% of 436 gigabytes off the top of your head. That's how much we can do every day for guest observers. Anyone in the world who wants to observe with PLATO and wants to observe their object for 2 years, bang, 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 continuously. Yes.
Question. Has the introduction of this spectroscopic analysis made SETI redundant or irrelevant now? Because I spent many years and keeping a computer running for 6 months and downloading a lot of data. Well, I've never heard much more about it, but I was involved with that for some time. But I'm just wondering whether that technique now is kind of being pushed into the sideline, that's all.
You don't hear so much about it. I'll let you into a secret. The computer in my office is also running SETI at home. And it's been running it for, it must be just after the project started. That has gone into the background just because so many years and they still haven't discovered anything. They have a few candidates that they've been following up, but so far nothing really good. The great thing is when you combine PLATO and then Ariel afterwards, which will follow up a couple of years behind us, Ariel, the James Webb Space Telescope, they'll be able to look at the atmosphere of candidate planets. PLATO will tell them these are the best, the most interesting targets to look at, and then they will follow up with their own instruments, and that actually may be a lot more successful than hoping that somebody on one of those planets has a radio transmitter and is actually bothering to beam a signal at us. We'll see. Actually, proving that there's life on a planet is not as simple as you might think, but there are various indicators in the atmosphere, oxygen, methane. They're both very strong hints that you've got life on a planet. If it's a small planet like Earth with methane in the atmosphere, it's very likely you've got microbes of some kind. So that may actually be the better way of trying to find life in the universe. There aren't many microbes with radio transmitters. Not that I've met, at least. Troublemaker in the back, I think. Okay, no, they've ignored him. Good.
The lesson from the solar system seems to be that not just planets in the Goldilocks zone are good for life, but maybe icy moons and things in outer planets.
Yes,
What about...
Emma was smiling a lot during the talk, which has me worried. Yes, I'm thinking in terms of Earth-like life, of course. People have got a lot more optimistic since then. Titan has a huge amount of methane in its atmosphere. One of the nobody quite knows where that methane's come from. One of the possibilities that has been planted, and I don't know if you think this is realistic or not, is that actually there's biomass under the surface that's releasing that methane. The methane gets destroyed rapidly. Do you think that is actually a plausible theory? Because I've certainly heard it proposed.
I have not heard that theory proposed. I have to say,
Okay, that's interesting.
but Titan's certainly very interesting. In terms
Titan
of
is very
potential
interesting
habitability.
because it looks so much like a primitive Earth. And of course, the ocean worlds like Europa, it seems that actually most of the Galilean satellites have probably got an ocean of some kind under the surface. We're getting more outrageously optimistic. So I'm being outrageously optimistic in one sense with Plato. Emma, I think, is going to give us some ideas in another sense. The icy moons, nobody would have imagined them as suitable for life even a few years ago. And then some guy called Arthur C. Clarke wrote an entire novel about it and populated Europa with all kinds of strange life forms. And the interesting thing is he might just be right, as he was with other things. But I think I'll listen to Emma and find out how plausible that is.
Ariel have already come up with a target list which are suitable for amateurs to observe transits. Will you be looking at those stars, or will you be issuing a target list of your own?
We'll have our target list because we've got our field of view, and we've got to observe what's in that field of view. Because the controllers of the Plato satellite are the Germans in Darmstadt. They are very protective of their satellites, and they have announced an edict that we are not pointing our satellite anywhere else in the sky, whatever we say. It will be pointed at that area of the sky. So yes, we'll have a target list, candidates, and we'll be asking people to confirm the candidates in that area.
Is there a link to this Austrian chap on your website?
There isn't at the moment because we're at very early days, but I can put you in contact with him.
Okay, thanks.
Any more? We've got about a couple more minutes before any more questions.
Any more for any more? Hidden at the back.
So we're looking for Earth-sized planets. We're looking for planets in the Goldilocks zone, but we're also looking for solar systems that are stable.
Yes.
And is there any way we can, we're not talking about hundreds of billions of years or hundreds of millions of years, but we could look for solar systems that are likely to be stable because there might be a Jupiter-sized planet whizzing around near the Earth-style planet. Are we close to that at all?
Well, certainly you can, if you know that you've got a Jupiter-sized planet close into the star, any small planets inside it are unlikely to be very stable for very long. So once you've picked up the map of the solar system, where the planets are, you'll know quite quickly how dynamically stable it is. And realistically, I think anything that has a 10 Jupiter mass planet in it, unless that planet is a very long way from the star or very, very close in, is not likely to be stable on any side. But once we know where the planets are and what their masses are, you can work out what the likely stability is. One of the surprises people have had looking at the stability is the fact that our solar system, the planets have been wobbling backwards and forwards a great deal since the solar system was formed. Uranus and Neptune were certainly not way out there where they are now, 4,500 million years ago. That's one of the surprises we've had, that planets do migrate and they get closer and more distant over time because these big planets shuffle them round. So that's something, yes, we do need to look at very carefully. So anyone else? One last question.
Could we ever detect planetary magnetic fields? Our own magnetic field is very important to the state of the current Earth.
That's a more tricky one. I can imagine ways that it might be possible to do it, but it would need instrumentation very much more sensitive than exists at the moment. However, if you had told me 30 years ago that amateur astronomers would be taking spectroscopy with a resolution of, you said, 20 meters? No, 20 years ago, no professional telescope could manage that. or very few professional telescopes can manage that. What is possible today and what might be possible in 20 years' time? It's very, very difficult to imagine. Astronomy and astronomical instrumentation has come on so fast. It is possible that we might be able to do it. Just the magnetic field split spectral lines. So if you can observe with high resolution, you can see the spectral lines splitting, that would allow you to detect the magnetic field, but you never do it with any earthly instrument now. So, you want to finish, wrap up?
Yeah,
Or?
I was going to say, that they normally say try and keep Mark under control time-wise, but I think you've done an exceptional job. So, thank you very much indeed, Mark. Very useful, and it's obviously going to tie in. Thanks so much indeed. And if Hazel has asked me to just give a quick mention that she's still selling some raffle tickets. We'll be drawing the raffle just after the next talk, just before the Sky Notes. So that's just outside, I think, £1 a ticket. And there's a variety of prizes that are just on the table there for you to look at. So it's just coming up to 1:45. If you'd like to come back in for about 10 past 4 for starting off again, when Emma will be talking about her work with in our own solar system, a bit nearer to home. Thank you very much indeed.
Yes, please, I'll be sitting down selling stuff.
They may set you up for a few questions.
So what does Emma have to do to
Because we were picking you up. And we had these. Yeah, that's the problem. The rooms. The things came well. We were going out into some of the other things. Yeah, every time you went away from it. Have you got
No. I would say, sorry, I'm just, yeah, so we just set up this. I'm going to use my own laptop.
Okay.
I'm just bringing it.
Can we try it on this? Only that the next one after you is all the other stuff's worked.
It's just that I've got movies embedded and stuff.
If they're embedded, it should work. It's a good laptop.
Yeah, well, it's embedded on my computer, and on the memory stick it's not, so I'd have to do all that again, so it would be a bit of
Can we not just take the copy off your laptop? And just, that means, because then otherwise we're not changing between you and the next presenter.
Okay, well, let's try.
Emma to have the priority.
Well, I'll tell you what, if I give you the memory stick, you can see if it works, and if it doesn't work, we'll use mine.
Because it works on...
Yeah, but it's on this case.
Yeah, I just don't want to have to faff about and putting things back into PowerPoint.
Emma, do you want... Which one is it? Yeah. I'll just drag that.
And there's one audio file, so...
I'll just go and make sure.
Is it that presentation?
Would you do that for the final recording?
Yeah.
What I'm going to do is take off presenter view.
No spoilers.
Hold on. I'm trying to get it off
Oh,
the
sorry,
screen.
don't worry about it. It's fine.
Can I just make a comment? Mark managed to accidentally turn his lapel mic off. So various people were saying that the sound level was going up and down because it was only coming through there. So if you just make sure that the lapel mic is on when you're talking.
Yep.
That'd be good.
Will do.
Was it live streaming? It was live streaming, yeah. Well, and people said it's really good. It's just the sound level. When he went over to the other screen. Yeah, when he was walking away, because he had a lapel mic, but he accidentally turned it off, so it was just going through the lectern mic. So I'll give him a kicking in a minute.
Yeah, we do that. And the thing is, when you've got a room voice that carries, it didn't matter in the room.
Yeah,
but it does
on
the stream.
Yeah.
And
the other thing too is when people are asking questions, it got right towards the end, but we do need to say to people, please, if you want to ask a question, wait for the microphone to turn up, because otherwise the people on the live stream can't hear you.
One of the problems with, I do a lot of webcasting, and if I'm doing something on demand, I always chop the questions off. But partly you need people's permission in the room, but two, just so when people come back before you introduce, if you can just press.
The slideshow button. Yeah.
I said that to the last guy, and he didn't.
So, okay. Oh, that's my microphone on.
Right. Cool.
Okay.
I'm going to grab a cup of tea.
Does that, can you pick that up at all? Is that any better? Yes or not? No? Is that any better? Can you hear? Oh, good. Can we test just whether your hearing loop is working? Is that any better? Excellent stuff. Thank you.
check. I was just told to press. No, I know what to do. Yeah, you just told me to press that. It's fine.
Okay, that's fine. Okay.
No worries.
Good afternoon, everybody. Hello. Is it working or not? Are we okay? Okay, thank you very much. Thank you. Excellent. So continuing a planetary theme, we've got Professor Emma Bunce. She's a planetary scientist working at the University of Leicester, and is the President-elect of the Royal Astronomical Society, and taking over in April. Is that right? May. Excellent stuff. So involved in multiple high-profile space missions, exploring our solar system, including Cassini, obviously, which is finished, Juno, Jupiter, Bepi Colombo at Mercury, and the future JUICE and the Jupiter, Icy Moons Explorer, which is obviously the subject of her talk this afternoon. She uses data from these missions to answer fundamental questions about these diverse solar system objects. She's the principal investigator on the instrument called the Mercury Imaging X-ray Spectrometer, part of the Bepi Colombo payload, launched to Mercury in October 2018. She played a key role in the definition of the proposals for the JUICE mission, and will be working on two of the instrument teams from that mission when it arrives in the Jupiter system in 2030. She's published approximately 120 scientific papers on solar system science and received multiple awards in recognition of her work, in particular recently receiving the 2018 Royal Astronomical Society Chapman Medal for her research on the gas giant planets. So if I can introduce to you, give a warm welcome to Professor Emma Bunce. Thank you.
Okay, thank you for that great introduction. So you've introduced me, so I don't need to do that part, so I'm just going to move straight on in the interest of time. I'm going to talk about oceans, ices and fire, the mysterious moons of Jupiter. Okay, so as you will all know, as you move out from the sun, Jupiter is the first of 4 gas giant planets in our solar system. And I always refer to Jupiter as the planet of superlatives, okay? So it's the largest planet in the solar system. It's about 11 times the size of the Earth. And it contains 2/3 of the mass of all the planets in the solar system put together. It rotates faster than any of the other planets. So despite its giant proportions, its day is just under 10 hours long, which is quite incredible. It takes 12 years for Jupiter to orbit around the Sun, as it lies 5 times further away from the Sun compared to the Earth. Okay, so it has the most dynamic atmosphere of all the planets. Got the laser pointer. And of course, it's famous for the Great Red Spot, which you can see here, a long-lived storm in the atmosphere that's been raging for hundreds of years, possibly even more, inside which you could actually fit 2 to 3 planet Earths. It gives you an idea of the scale of the Great Red Spot. And It's got 60 or over 60 different moons. Many of them are very small and quite faint and you know, don't even have names. But 4 of them are incredibly famous. And in fact, the more we learn about these mysterious moons of Jupiter, the more we sort of change our view of the way the universe actually works. So here they are. I'm going to introduce you to the most spectacular of Jupiter's moons. We've got fiery Io, the bottom left. We've got smooth, icy Europa, which you can see just there. We've got planet-sized Ganymede, and we've got scar-covered Callisto. So I'm going to give you a little bit of insight into each of those bodies in this talk. And these moons were discovered just over 400 years ago, and since that time, they've been studied with backyard telescopes, by spacecraft en route to faraway destinations like the Voyager mission, and they've also been investigated by dedicated missions such as Galileo in orbit around Jupiter. So I'm going to come to all of that in a moment, but what I'd first of all like to do is to go back in time. I just want to show you something really fun. So as I'm sure you all know, just over 400 years ago, in 1609, this amazing scientist, Galileo Galilei, was designing a telescope, designing a better telescope than was currently being used elsewhere in Europe. And importantly, what he did with that telescope would literally change the way we view the universe forever. So at the time, the popular belief was that the Earth was the orbital center of all the celestial bodies. Okay, so the geocentric model. And what he did with his observations was to change that view. Okay, so let's just have a quick look at what he did specifically with the Jupiter system. So in the top left is actually Galileo's journal. So you can see scribblings, I can't read them, and drawings of his observations that he was making at the time. And on the right-hand side, you've got an example of the publication of those observations in Sidereus Nuncius, and that was published in March of 1610. Now, at the bottom, what I'm going to be showing you are a reproduction of those sketches. So the asterisks and the circles are actually reproductions of Galileo's drawings from those observations that he made in 1609. And just above that, you can see, hopefully you can just about see, there is Jupiter at the center and 4 objects. Now, those are actual calculations that, because we now understand the Galilean moons and how they work and how they orbit, those are calculations of where those moons would have been at the time of those observations. So we can do a comparison between what Galileo saw and what we now understand from our knowledge of those bodies. And I think this is really quite neat. Obviously, I'm terribly overexcited about it. Okay, so you can see on the first night, the 7th of January, Galileo made an observation, and he noted in his journal that he was quite surprised to see Jupiter in amongst 3 stars that all seemed to be aligned with the ecliptic. The next night, on the 8th of January, he made a second observation, and he noted, with some surprise, that these 3 objects were now to the right-hand side of Jupiter, and indeed, on the next night, to the left-hand side of Jupiter. And this confused him, because as far as he was concerned, these were stars. And yet, Jupiter seemed to be moving the wrong way relative to those background stars, and indeed zigzagging across his field of view. And actually, he noted as early as this observation that he thought that these stars were following Jupiter. Okay, on the next night, I just want to point this one out because I think it's quite interesting. You can see here that he's drawn Jupiter and 2 stars, and as you can see from the model prediction of where the moons actually are at that time, you can see that 2 of them are transiting Jupiter, and so he couldn't resolve those observations, and so he saw 2 only and Jupiter. I think that's really neat, talking about transits that you were hearing from earlier. Finally, on the 13th of January, Galileo actually resolves 4 objects for the first time, okay? So that's really great. So now I've got a quick movie of all of the observations. He made 64 observations of the positions of these 4 stars relative to Jupiter between January and March in 8 weeks of observations. And during that time, he actually worked out their relative sizes and he worked out their orbital distances, and he came to the conclusion that they were not stars. They were following Jupiter across the sky, and his prediction was that they were indeed in orbit around Jupiter. Now, as you all know, what he discovered and would later become known as the Galilean moons, Io, Europa, Ganymede and Callisto. And of course, what he did was to show that not every celestial body was orbiting the Earth, found evidence to support the Copernican or heliocentric model. And of course, as I'm sure you know, the history made him rather unpopular. Okay, so let's fast forward back in time to present day and think about, so those are remote observations using a telescope. You've heard Mark talking about observing exoplanets. But what about if we can actually go to the body? What about if we can send a spacecraft somewhere? How much more do we expect to learn? So if we can send a spacecraft to travel through the solar system like the Voyager mission, or indeed like the NASA Galileo mission, then of course we significantly improve the view. So you can see here the basic outline of the Galilean moons. Let me just put the next little bit of information on. Okay, so closest to Jupiter then we have Io. And Io is about 3,643 kilometers across. So it's not that different from the size of our own moon. And it orbits at around 6 Jupiter radius. So just to give you an idea of the scale size of Jupiter, a Jupiter radius is 71,400 kilometers, approximately speaking. And as you can see there, the orbital period of Io around Jupiter is 1.8 days. Okay, next we have Europa, slightly smaller than Io, and at an orbital distance of just under 10 Jupiter radius, and orbits with a period of 3.6 days. Okay, then we have planet-sized Ganymede, 5,262 kilometers across. Ganymede is actually bigger than Mercury. That's one of the other missions that I work on. So Ganymede is similar to Mercury in a few interesting ways. It orbits at around 15 Jupiter radius and has an orbit period of 7.2 days. Okay, and then we have Callisto, the furthest away from Jupiter. Callisto is actually the 3rd largest moon in the solar system, Ganymede the largest, Titan in between, and is 4,821 kilometers across and orbits at 16.7 day orbit around Jupiter. So why am I telling you all these numbers? I'm sure that some of you are keen-eyed and have spotted the relationship between the orbit periods of some of these moons. So you can see that there is, we're multiplying up as we move out from Io to Europa to Ganymede. And that actually plays a crucial role in the way the system behaves. And I'm going to come back to that in just a moment. In fact, I'm going to come back to it right now. Okay, so there's 2 really important factors in the Jupiter system. And the first is the effect of gravity. So that's what we were just seeing there in those numbers, the orbital periods being a multiplication factor of each other. Okay, so we've got Io whizzing around close to Jupiter, and then Europa outside of that, and Ganymede outside of that. So for every 4 orbits of Jupiter that Io makes, Europa makes 2, and Ganymede makes 1. Okay, so this is called the Laplace resonance. This is a very special resonance that the moons are in, and it has a really interesting effect on the bodies. So obviously, the presence of the very large planet Jupiter in the system has a significant gravitational effect on the bodies, but actually, they are significant sized moons themselves moving around in the system, and they also affect each other. And so this resonance pattern actually produces a pushing and pulling motion on the individual moons, and we tend to refer to these as solid tides. Okay, so it's like the tidal interaction that you get between the Earth and the Moon. And on Io, you might be surprised to hear that the solid tide or the motion of the surface of Io, is thought to be up to 100 meters. So the interaction between Io and the other moons and Jupiter produces this pushing and pulling of the surface. And again, at Europa, the solid tide is thought to be 30 meters. And so that effect gets smaller as you move further away. Now, of course, this has a very important effect on the interiors of these moons, and in fact provides tidal heating to the interiors of those bodies. And I'm going to come back to that in just a moment. The second really interesting effect is the effect of electromagnetism. And this is one of my favourite topics. My field of expertise in terms of the gas giants is in space plasma physics, looking at magnetic fields and aurora. Okay, so just to quickly describe to you the situation, as I say, Jupiter is the planet of superlatives. You won't be surprised to hear it also has the strongest magnetic field of all the planets in the solar system by a long way. And that magnetic field, well, we're learning more about it actually from the Juno mission, but that magnetic field is generated deep within Jupiter itself. And as Jupiter is rotating very quickly every 10 hours, so the magnetic field is also rotating very fast. Okay, so that magnetic field of Jupiter extends out into the surrounding regions, and we call this the magnetosphere. Guess what? Jupiter's magnetosphere is the largest magnetosphere in the solar system. You're sitting in a magnetosphere right now, but it works in a very different way to Jupiter's. So Jupiter's large magnetosphere is rotating around rapidly, approximately once every 10 hours. But the moons are moving more slowly around Jupiter, and so you have a magnetic field which is sweeping past the moons, interacting with those moons, and producing some very interesting effects. Okay, so let's go through each of the bodies in turn. So first of all, let's think about Io. Io is the closest of the Galilean moons to Jupiter, and is rather bizarre looking actually when you get a really good photograph of it. I always wonder what Galileo would have thought of these pictures from the Galileo mission, named after him, obviously. And so Io is this sort of yellowy looking kind of pizza-ish type moon. It looks a bit like a rather unappetizing pizza, but is covered with these dark spots and covered in a sort of yellow material. It's actually a very young and smooth surface. And as I mentioned already, it's subject to some of the strongest tidal forces of all the moons, and flexing of that surface, producing heat in the interior. Now, in turn, what that does is to produce a magma ocean underneath the surface crust and produces active volcanoes. In fact, Io is the most volcanically active body in the solar system. And these volcanoes were discovered by the Voyager flybys that took place in the 1970s. And you can see the picture on the right-hand side there that was analysed by scientists looking at this data as it was coming in from the Jupiter system. And I know that when that picture first came in, people were not sure. They just thought there was something wrong with the camera. You know, there was a bad pixel or something occurring, that there was a bad image of Io, and were not expecting at all to have captured a volcano in erupting on Io's surface. And so our understanding now is that Io has this magma ocean underneath the crust and is producing these active volcanoes. In fact, there are thought to be over 400 active volcanoes on Io. And this is a little movie that was taken by the New Horizons spacecraft on its way to Pluto, actually showing one of the volcanoes, Tvashtar, in the north there. You can actually see that is a movie of the eruption of that volcano as the spacecraft flew past, which is pretty amazing. Okay, so actually, incredibly, those volcanoes produce around a ton per second of material continuously from those volcanic eruptions. So Io moving around near to Jupiter is like having an active comet orbiting around Jupiter, thinking about the amount of material that's being produced. So what happens to that material? Well, initially the material is of course neutral. It's coming from within Io. It's mostly sulfur and oxygen, sulfur dioxide, gas. But what you can see in these pictures here is that that material forms what we call a torus. Okay, so the neutral material is surrounding Io, and as Io moves around Jupiter, it forms a path of neutral material, and over time, those neutrals become ionized by photoionization or electron impact ionization and produces a plasma torus. Okay, so then we have a plasma torus surrounding Io all the way around planet Jupiter. And this produces some very interesting effects indeed. So first of all, we have Io moving along its orbit at around 17 kilometers per second. And we then have Jupiter rotating around with its magnetic field at the orbit of Io at about 75 kilometers per second. And so we then have a situation where we have effectively a conductor, Io in its plasma torus, sitting in a very large, strong magnetic field which is rotating around. And this actually produces a perturbation along the magnetic field lines which are connecting Io to Jupiter, and that perturbation is carried by an electric current that then connects Io to the upper atmosphere of Jupiter. So it feels a bit like science fiction at this stage, but I promise you it's not. So there's just another little sketch of what I'm talking about. We've got this plasma torus going all the way around where Io is orbiting around Jupiter, and then where these magnetic field lines are passing through Io, and we have a conductor moving around relative in a magnetic field, generate a really interesting interaction. And let me show you what that looks like in Jupiter's upper atmosphere. So this is a picture taken by the Hubble Space Telescope, one of our favourite telescopes to use. We do lots of observations of Jupiter and Saturn in ultraviolet wavelengths, specifically looking for auroral emissions. Okay, so this is Jupiter's northern auroral emission. And what I want to point out first of all is on the left-hand side, you can see a spot, and you can also see a trail coming behind, and that is actually the footprint of Io. So that's the interaction between that conducting body moving in a magnetic field that set up an electric current, which then is communicating with the upper atmosphere of Jupiter. Okay. So now I've just put in a picture of the Earth, and you can see Earth's auroral oval as well. And actually that's sort of roughly to scale. So you can see that you can fit approximately 2 to 3 Earths across Jupiter's northern auroral zone, which again is sort of mind-blowing. These are enormously powerful, guess what? The most powerful auroras in the solar system, by 1,000 times stronger than the Earth's, and take up a huge amount of latitude in Jupiter's polar region. And I can just point out a few features. So I've pointed out Io already, and we also have 2 more spots which are relating to Europa and Ganymede. And we then have what I've labelled the main auroral oval. And it's not quite an oval, so we can talk about that. But you can see on the left-hand side it's quite smooth. You can see what looks like a fairly clear auroral oval, and then on the right-hand side it becomes a complete mesh. You can ask me about that later. I'm not going to have time to go into that. And then within that main auroral oval region, we also have something which have been labelled the polar emissions. Very imaginative labelling here. This is because we don't really know what causes the polar emissions, and we still actually don't know. This is one of the things that Juno is currently studying and we are actively working on. But in order to describe to you how the main auroral oval works, which is actually still relating to Io, I'm just going to take a moment to describe what the magnetosphere actually is. So a magnetosphere is formed as a result of the interaction between the Sun and any planet that has a magnetic field, an internally driven magnetic field. So we have intense heat in the upper layers of the sun's atmosphere, which causes the gas from the sun to become ionized and then to flow continuously into space, and that's known as the solar wind. And the solar wind carries with it the sun's magnetic field, and so the solar wind and the sun's magnetic field moves out throughout the solar system and interacts with any planet that has its own magnetic field. And what it does as it approaches a planet with a magnetic field is to squash the planet's field on one side and stretch it out into a long tail on the other side. Now, the Earth's magnetosphere, which we understand pretty well, is driven by a process known as magnetic reconnection, and that process takes place at that first point of contact between the solar wind and its magnetic field and the planet's magnetic field. And that reconnection process drives a series of events, and one of the manifestations of that interaction is the Earth's aurora. So if you've seen the Earth's aurora, that is solar wind magnetosphere interactions in action. Now, Jupiter doesn't quite work in the same way, although it does have aurora, which look, on the face of it, relatively similar to the Earth's. Jupiter's magnetosphere, as I've already mentioned, is the largest in the solar system. And in fact, just as an interesting point, it's thought that that solar wind interaction with Jupiter's magnetic field is thought to extend all the way to Saturn's orbit. One of the Voyager flybys, it was thought that maybe Saturn was even within the magnetotail of Jupiter, and that changed the sort of interaction that we were seeing between the solar wind and Saturn at the time. Okay, so Jupiter's magnetosphere is dominated by rotation, as I've already mentioned. So Jupiter is rapidly rotating. And the other important fact for Jupiter is the fact that we have this comet, which is orbiting around Io. We've got this plasma source. So what happens next? Okay, so we have a ton per second of material that's being continuously put into the Jupiter system. So if you add mass to the system, then actually in a rapidly spinning system, it actually wants to move outwards, okay? So the plasma associated with Io actually moves continuously away from Jupiter and forms the sort of red bit of the cartoon you can see there, which is known as the magnetodisk. Now, as it does that stretching out, as the plasma moves outwards away from Jupiter, it stretches the magnetic field line. So you can see I've drawn some solid white lines. Those are the magnetic field lines of Jupiter. And as the plasma's moving out, it's stretching out Jupiter's field. And it's still all spinning around, or trying to, once every 10 hours. So this is an enormous, scale size that we're talking about here. And this plasma and magnetic field is trying to keep up. Well, funnily enough, it finds that quite difficult. The ionosphere is helping out by communicating a torque actually along the magnetic field line to the equatorial plasma to keep it spinning, but it can't quite keep that process working. And so eventually what happens is that the plasma starts to slow down compared to that rotation rate. And we call that the breakdown of co-rotation. So it's a fancy way of saying that it can't keep up. Okay, and what that does is it actually causes the magnetic field lines to bend backwards. So they're sort of dragging behind as they're trying to spin around. And if you know anything about electromagnetism, you'll know that if you bend the field, you're going to generate a current system. Okay, so now we've got a situation where the field is dragging behind. We generate an electric current system. That's the dashed lines in that diagram. And we have upward directed current, outward directed current at the equator in the red region, and then back towards the planet and closing across in the upper atmosphere. And it's actually where you can see that red arrow pointing, it's actually that upward directed electric current, downgoing electrons that are being accelerated into Jupiter's atmosphere that's actually thought to produce that main auroral oval. Okay, so this is sort of mind-blowing, I think. I'm completely biased because you can probably see at the bottom, this was the subject of my PhD thesis, so that's why I'm so enthusiastic about it. Okay, so we have this process, this strange situation whereby we have a plasma source, Io, in a magnetosphere, Io's orbiting around close to Jupiter, Jupiter's magnetic field is spinning around, and the interaction between those produces the brightest aurora in the solar system. So for the person who asked the question about whether you could measure magnetic fields remotely, one way you could do it is to look at evidence for emissions associated with aurora, like radio emissions or, for example. Okay, and people are actively thinking about doing that. Okay, so little Io, the tail wagging the biggest dog in the solar system. Okay, let's move on to Europa. Okay, so Europa has this stunning surface geology. I think this is one of the most amazing pictures of Europa, again, taken from the Galileo mission. It has a smooth, icy surface, not many craters, which means that it's young, it's being replenished, and it's thought that there is an ocean beneath the icy crust. And you may be aware, or you may not be aware, that in fact the first evidence for that subsurface ocean actually comes from magnetic field observations. So that was discovered by the Galileo mission, and as the spacecraft moved close to Europa, the magnetic field instrument, the magnetometer on board the Galileo mission, measured changes in the field direction which could not be explained by an internally driven magnetic field at Europa, or indeed by Jupiter's background magnetic field. I'm sort of wrapping it up in a few sentences. It was many years of work to get to the point that it was understood that those magnetic signatures are actually the signature of an induced magnetic field. Okay, so the idea is that the subsurface ocean underneath that icy crust is conducting, capable of conducting electric currents. And again, you have Europa moving around in a larger, strong magnetic field, which is also varying in time. And it's that variability in time that allowed the understanding that this was an induced signature. So it sort of flip-flop back and forth as Jupiter's field rotated around. Kind of hard to imagine. And this is the amazing lady who did the work, Margaret Kivelson. She won the gold medal of the RAS this year, was presented with the medal this year. She turned 90 this year. She's an absolutely amazing woman. I have a huge amount of admiration for her, and she's still working on Europa Clipper, which is hugely exciting for her. You know, she discovered these signatures from the Galileo mission, and now she's still working on the next mission to go back to Europa and find out more. Okay, so it's thought from those magnetic measurements that Europa's ocean is 10 times deeper than any ocean here on Earth, so maybe 100 kilometers deep. Now that is incredible. I get my first year tutorial group to work this out. What does that imply for the volume of water? It implies that there could be 2 to 4 times as much water in that subsurface ocean than there is here on planet Earth. And so, as you can imagine, tidal interactions producing warmth that enables the liquid, the water to remain liquid. And we also wonder or think that Europa's ocean may be in contact with a silicate floor, and that could explain some of the markings that you see on Europa's surface. It could be organic materials. And hence we then start to think about the opportunities that might exist for habitability of that subsurface ocean. We know that here on Earth we find life where you really wouldn't expect to find life. In the deepest parts of the ocean where there is no sunlight. Okay, so moving on to Ganymede, planet-sized Ganymede, for me is one of the most fascinating of the Galilean moons because it seems to sort of have everything. It's got these really diverse features. So it has the largest number of impact craters of any planetary body in the solar system, and it's also thought to harbour a subsurface ocean. And in addition to that, it also has its own magnetic field. So a magnetic field that's generated internally to Ganymede. So Ganymede's subsurface ocean is thought to be a little more complex than Europa's, and possibly in different layers. I've seen multiple versions of this diagram with ice layers and water layers and what have you. But actually, what we really need to do in order to understand what's lurking underneath Ganymede's icy crust is to actually put a spacecraft into orbit. And once you have a spacecraft in orbit around Ganymede, then you can start to understand the details of how the mass is distributed throughout the interior. So the observations again from the Galileo mission, again, Margaret Kibbleston made the discovery using the magnetic field data. First of all, measured this small, relatively small perturbation in the magnetic field, which is an induced magnetic field, an induced current system associated with a subsurface ocean. But then over time, the measurements also indicated that there was a stable component to that magnetic field, so one that didn't flip-flop depending on where Ganymede was relative to Jupiter's magnetic field. And that indicated that Ganymede actually has its own internally generated magnetic field. So the only moon that we know in the solar system that has an internal magnetic field. Now, if you then take a moon with its own magnetic field and put it in a larger magnetic field, you end up with a miniature magnetosphere within a magnetosphere. So it's all good stuff. So there you can see we've got little Ganymede, although it's big, large Ganymede, planet-sized Ganymede, in Jupiter's magnetic environment, and Jupiter's magnetic field interacts with Ganymede's and produces a magnetosphere. Okay, now I'm hoping this is going to work. So these are, I just want to play this to you because I think it's just one of the best things ever. This is Galileo plasma wave measurement. So we've got a frequency time spectrogram. So this is the data that I'm going to play to you. Okay, so this is not actually measured at audible wavelengths, but if you just shift them, then you can listen to them. Okay, so a little bit of artistic license, but I think it's worth it. Okay, so this magnetic field and magnetosphere was really understood by using these measurements. Let me start playing it. It might be quite loud, so brace yourselves. So that noise is the spacecraft crossing through the boundary of the magnetosphere. And now you can hear the rising frequencies get close to Ganymede and the field strength gets stronger. You can hear the particles rotating around on those field lines and their frequencies change as you move through a stronger or weaker magnetic field. You can hear those really high pitches and then they start to come down as the spacecraft moves away and the field gets weaker. So we can hear that in a second. Okay, I'll make it stop. I just love listening to it. So Margaret Kibbleston referred to that as Ganymede's singing magnetosphere. So you could hear the particles singing on the magnetic field lines. Okay, Ganymede also has its own auroral display in its weak atmosphere measured by the Hubble Space Telescope and the footprint that I mentioned to you earlier. Finally, we have Callisto, which is, well, another fascinating object in its own right. It's a heavily cratered ancient surface. It is thought to have an undifferentiated interior, so that's pretty unusual, and that's based on gravitational measurements, so we need to find out more about Callisto to really understand its interior. And it is also thought, from the magnetic observations again, that it might have a subsurface ocean. So there's water everywhere in the outer solar system. You can also see Valhalla here. I'll try not to fall off the stage. You can just see the sort of central point of that impact crater there, and you may be able to work out multiple concentric rings. It's one of the biggest, it is the biggest impact crater in the whole solar system. Okay, so as you can imagine, all of this water, so excluding Io, because there's lots of lava and volcanoes and definitely not a holiday spot. So then we have Europa and Ganymede and Callisto, which are all thought to have subsurface oceans. And so if you're interested in thinking about the potential for habitability, whether that be in the past or in the present, then these ocean-bearing worlds are obviously of great interest. So what we need to do is go there and make more detailed measurements. And this is where JUICE comes in, the Jupiter Icy Moons Explorer, a very strange acronym, which is a long story in itself. I was lucky enough to be invited by the European Space Agency to be on the team of scientists that defined the mission. So it's absolutely one of the highlights of my career so far. And we worked very hard on the mission, designing it to go to the Jupiter system, and specifically to go into orbit around Ganymede as a focus of that mission. And there is also a NASA mission called Europa Clipper, which is going to go and focus on Europa. Okay? But JUICE will not only look at Ganymede, it will also look at Jupiter. And so there's a huge amount more that we can learn about the system. Important facts are, talking of patience, JUICE is going to be launched in 2022. The mission was accepted in 2012, and it will be hopefully launched, or yeah, it will be launched in 2022. And because I'm really impatient for it to arrive at Jupiter in 2030, so we have to wait a really long time. If you're a planetary scientist, you have to be extremely patient. And we're going to get opportunities to do a couple of flybys of Europa, multiple flybys of Callisto and Ganymede, before being the first mission to go into an orbit around an icy moon. Okay, so I think I've basically mentioned all of this. This is just a sort of timeline of activities where we will focus on Jupiter itself at the first part of the mission, moving to studies of Europa. We've got 10 Callisto gravity assists, which will give us a fantastic opportunity to study Callisto, and multiple visits of Ganymede before we finally go into orbit around Ganymede, and at the smallest orbit, we will get to within 500 kilometers of the surface of Ganymede. So, you know, just wait for those images and information that we will get from that mission. Now, you've already heard about the habitable zone, so I don't have to spend a lot of time on this, but as we heard earlier, you know, we're typically interested in where you can have liquid water on the surface. But what I hope I've shown you is that you can have liquid water underneath the surface. So unlike looking for Earth-like planets that we were hearing about from PLATO, this mission is looking at habitability in the more general sense. So we're interested in these deep habitats. We have them in the Jupiter system. We also have them in the Saturn system. We've got Enceladus spewing water out into Saturn's magnetic environment. We've got Titan, which is thought to have a subsurface ocean. So it gives you a different perspective on this concept of the habitable zone. And there's my sort of link to what our mission can contribute to our understanding of exoplanets. I mean, absolutely fascinating subject, and it's changing all the time in terms of the numbers of planets that we have confirmed and the nature of those planets, and we've been hearing a lot more about that today. But my argument has always been that our own solar system we can go to, and we can actually go to and make close-up studies of these moons, and I think we should really exploit that opportunity of studying our own backyard, as it were. Okay, so there's just an overview of all the different science that we're going to do. We're going to look at Jupiter. We're going to look at these coupling processes that I've told you about, gravitational and electromagnetic, and look in more detail at the nature of these subsurface oceans which exist at these moons. And our justification slide at the end of our presentation when getting this mission selected was that we felt it was the next logical step in our exploration. We have the discovery of the Galileo moons from Galileo back in 1610. We've had the first visits from the Voyager missions, those amazing spacecraft that are still going, still giving us new information about our local environment. We've discovered that there are deep habitats here on this planet which are able to survive without sunlight. We've then had exploration from the Galileo mission at Jupiter, the Cassini mission at Saturn, and discoveries of potential water worlds in extrasolar systems. And so now is the time. As you can tell, this is my pitch, but it's okay because the mission is happening. It was selected, yes. So now is the time to go back and really characterise these bodies and learn the next level of understanding and discovery about the subsurface oceans. So I always think of Galileo. I think of how far we've come, and I wonder what he would think if he knew that this was the kind of thing that we were now able to do. So thanks very much for listening.
Thanks so much indeed, Emma. That was very good. Thank you.
Thank you.
As expected, it's wonderful. We've got about 10 minutes or so. Are you okay to answer some questions?
I'll do my best.
What I would say, if I may, is that because this is being videoed and being live streamed in actual fact, if you sort of get selected to ask a question, if we can wander around and give the microphone to you, because whilst we can hear you in the room, it's actually a little bit difficult for people elsewhere. So have we got any I'd like to take the microphone over. Thank you.
Thank you, very interesting. Have you any idea of what the temperature of the oceans might be?
Oh, that's a very good question. No, I don't think that we have any, in the Jupiter system, I don't think we have any direct measurements as yet. The Hubble Space Telescope has actually recently confirmed that there could be plumes at Europa, similar to the plumes that we have at Enceladus. So that's been a fairly recent discovery. And I'm trying to remember the numbers from Enceladus, but I mean, cold is the answer. Really cold. No, I think, to be honest with you, I think until we have measurements from orbit, and specifically with infrared spectroscopy, that we won't really be able to say much more until then. But the nature of those subsurface oceans, definitely not my field of expertise, is very interesting. Like how does the water remain liquid? How could you possibly have layers of ice and water and ice? I don't know the answer to that. But the gravitational measurements give us an indication of that distribution of mass. And so again, I think when we have data from orbit, multiple orbits going around and around Ganymede, we'll be able to build up that picture of the gravitational field with remote sensing, ultraviolet, infrared, and that will really help us to get close to that. But I suspect, you know, if we'd like a direct measurement, then we need a future mission to Europa or Ganymede, or both, that would actually put a lander down onto the surface. And I think that, well, I know that that's already what people are thinking about for the future. The next logical step.
David at the front.
With all these complicated magnetic fields on Ganymede and Jupiter and so on, and these likely conductive oceans, I would expect there'd be lots of electric currents in these oceans, which is something that we've got no analogue for on Earth. So, and I would have thought that would have a bearing on whether they could support life. Do you have any thoughts about that?
That's a good question. No, I've never thought of it in those terms, if I'm honest with you. The currents are not particularly strong, actually. I mean, I'm trying to think of the numbers for the current that's flowing between Io and Jupiter, for example, is about a microamp per meter squared. So they're not particularly strong currents. I mean, they are in space plasma physics terms. So that's a similar current strength, actually, to the current at the Earth that produces the aurora. But whether that would have any significant effect on habitability, I think is a very good question. I don't know.
Oh, sorry. Ah, you ask him there, can't you?
Hello.
Hi. Yeah, I like the idea of getting our first year tutees to calculate the.
Oh, yeah, you need to get them to do that.
I'm going to nick that off you on Monday,
yeah,
actually. But I was just wondering, is it still thought that the metallic ocean at the centre of Jupiter, this is responsible for the magnetic field, and do we know how it's done?
Good question, and very relevant, because the Juno mission, which you may have heard of, is a current NASA mission which is at Jupiter now, and is in an orbit which is specifically designed to study very close to Jupiter, as in frighteningly close to Jupiter, a few thousand kilometres above the cloud tops at closest approach in each of elliptical orbits around Jupiter. And what we've learned so far from that mission is that Jupiter's magnetic field is much more complicated, of course, than we had previously thought. So the idea is that the postulation is that the magnetic field is generated by liquid metallic hydrogen, highly pressurized layer of liquid metallic hydrogen within Jupiter somewhere. And the question was, where? Okay, and so one of the things that Juno wanted to work out was, could you work out where that generation of the magnetic field was? The results so far suggest, interestingly, that there may actually be two different depths that the magnetic field is coming from. So when you look at Jupiter's magnetic field, it's like no other planet in the solar system. Actually, I would say at this point, having studied magnetic fields at planets, interesting thing about our solar system is that each planet's magnetic field is really just unique. They're not like each other. And so if we think we understand how magnetic fields are generated in general, I think what we're learning by exploring the planets up close is that actually we perhaps need to rewrite our theories, our ideas. Anyway, to go back to your question, it's thought that that process is quite likely to be happening at Jupiter, but there could also be another layer where a magnetic field is being generated. And the reason that that's thought to be the case is because we see the details of Jupiter's magnetic field. You know, we think about it being a dipole, the sort of classic thing you do at school with your iron filings and your dipole, you know, bar magnet, and you get your loops of field, and that's what you think a planetary magnetic field looks like, which, you know, to a large part it does. Not at Jupiter. It looks so different, and it has, the next one up is a quadrupole, and then an octupole, and then it goes up and up and up and up in order and complexity, and you can think of that as being sort of multiple loops of the field. And we see so many high-order fields at Jupiter which are strong, and it's in the mathematics, you'd love it. It falls off as 1 over r to the 4, 5, 6, 7, 8 as you go up in complexity. But you see those higher order terms, which implies that they must be generated quite close to the top of the atmosphere.
That's remarkable.
Yeah, it's amazing.
We've been talking about the magnetic field, and it strikes me that water has got protons, and if you've got protons in a powerful magnetic field, you can have nuclear magnetic resonance. Now, for nuclear magnetic resonance, you need radio waves, but Jupiter is also a powerful producer of radio waves, and also, if you have an orbiting spacecraft, it could bombard the moon with radio waves. So I'm just wondering if there's any potential here to use NMR not only to find out about the nature of water in these planets, but given that organic compounds also display NMR, you could use it to detect organic compounds.
Yeah, very interesting. Very interesting. So one of the instruments on Juno, I'm going to sidestep the question because I don't know the answer. but one of the instruments on Juno is looking for water in the atmosphere. And it's a microwave radiometer, and it's the first type of instrument like that, and it works at, I think, 6 different wavelengths, and it has these arrays on the side of the spacecraft that are all different sizes that are measuring different frequencies coming from the atmosphere, indicating different layers. So there is already the technology to try to get those water and ammonia, actually, for Jupiter, measurements from within the atmosphere, but I don't know the answer to your very interesting question.
I mean, a powerful magnetic field is a crucial thing.
It is a crucial thing, yeah, absolutely. And it's a very powerful magnetic field.
About 5 minutes more, I think.
Yeah, on the time frequency plot that was behind when you were playing the singing ionosphere,
Yes.
towards the right-hand end there appeared to be a harmonic structure which was not present initially. There were multiple bands at intervals. I've seen that in acoustic spectra.
Yeah, well, you see a lot of...
Yes, on the right there.
Yeah, absolutely.
Do you know what's going on there?
I mean, it will either be... So if you can just about make out there's like a peak in the emission that you're seeing there, so that will be the closest approach of the spacecraft to Ganymede, and where the field is strongest and where the plasma frequency has peaked as you get to the strongest magnetic field, and then it's falling off, and then you're seeing multiple frequencies. Now, what that would normally indicate, and I can't say for sure that that's what that is, what that would normally indicate in space plasma physics would be the presence of some sort of wave-particle interaction, and then, of course, you can have multiple frequencies present and harmonics present, and we see that a lot, actually, in magnetic field studies of the Earth. So it's kind of interesting to see that Ganymede's magnetosphere is really quite a sort of miniature version. It might be more like the Earth's magnetosphere than like Jupiter's magnetosphere, but with some interesting differences in the sense that Jupiter's magnetosphere is driving Ganymede's magnetosphere, and so the Sun's magnetic field interacts with the Earth's magnetosphere and it changes direction, it moves around. Jupiter's is the planetary magnetic field, so it's always pointing in the same sense. And so it's like a continuously driven system. So it's a quite unique situation. So when we get there, the first part of the orbit of JUICE is actually to really study this magnetosphere in more detail. So the close 500-kilometre altitude orbit is to look at the surface and to get the magnetic field and the gravitational field of Ganymede itself. And before that, we have an elliptical orbit where we will actually be crossing through all of these regions of interest where we have this interaction, and where I imagine we'll be seeing a lot more of that interesting data and listening to Ganymede singing.
Thank you.
Excellent stuff. I think we've just about run out of time now because Hazel's frowning. Thank you very much indeed, yet again. Can I ask you, before you... I can ask Emma to draw the raffle ticket, if I may.
I'm afraid this is something that you're not supposed to do. It's very exciting. Just one?
Well, there's three things.
Okay.
So we've got an orange ticket.
It's an orange 47. Who's the lucky winner? Come and get one.
Oh,
Fix.
Have we got a clicker? This is
genuine, isn't it?
Yeah, that's grand.
Ah, does that mean I'm released?
Thank you very much.
Don't
think it's
mine. It's a pink number 6. Pink number 6.
Given meteorites, it would be, it has to be.
Where do you want to put it? Take this off. Yeah.
Okay, pink again.
It's all right? Yeah, it's fine.
This is fixed. This is our treasurer here.
Another pink, number 15.
Aha, you're not on cancel, are you? You're not on cancel.
That's the prize. This is very suspicious. Oh, yeah. Oh, do I need to speak louder? 1, 2, 3. Can you hear me on that?
Orange. 28. Orange 28? Oh, brilliant. Right, well, thank you all very much. And I hope that
Shall I just get going then? Right. Okay, so this is the kind of squishy bit at the end of the meeting where I'm going to entertain you for about 30 minutes with some pretty pictures and some interesting stuff of what's happened in the sky over the last few months and what's going to happen over the next few months. So hands up everybody who's seen Venus so far in this apparition. So a pretty large number. You'll know that it's at a fairly far south declination at the moment, so it's kind of scurrying along close to the horizon, but it will be becoming easier to see later. This is a lovely picture of 3 planets here. So you've got Jupiter down the bottom here, Venus, and Saturn's just up there, and of course the crescent moon. So this was, when was it, 29th of December, so just at the end of last month. On the odd occasions we get clear sky in the evening, just go out, look to the west, very low down Venus, but it'll be getting higher in the sky, and I'll come back to that in a minute. So normally in these sky notes we start with this fascinating object at the centre of the solar system. Sorry, Lynn. This is, of course, our sun, which is Jupiter may be the biggest at everything planet-wise, but obviously the sun is the biggest in our solar system, and it generates all of its magnetic field and solar wind and everything, but it manages to do all of that at the moment without actually generating any sunspots, which is a bit of a shame if you're into solar observing. But of course you can use hydrogen alpha, and there have been a few prominences recently. This rather nice one by David Strange a couple of days ago, coming out from the limb of the sun. And of course, all of that material that comes out of the sun, the solar wind, interacts with our magnetic field, which is definitely fairly puny compared to Jupiter's, but produces some very nice displays. And Gordon Mackey up in Scotland always manages to get some fantastic photographs. I like showing them at the Christmas meetings. They're just so good. This is polar star trails with an aurora thrown in for good measure. And he's actually illuminated that cairn in front with an LED light just to get a really nice effect. So, you know, astrophotography can go all the way from sort of really deep scientific and technical images of the sky to something like this, which I just think is an absolutely wonderful image, just capturing the whole beauty of the night sky. If you look at this closely, there is a satellite trail in it, and I'll come to that in a minute, as you might imagine. But I won't say anything nasty about Elon Musk because he can get quite angry and he might be watching the live stream. Anyway, yeah, so we still get reasonably good aurora, even though the sun's not very active at the moment. We're still getting a lot of good aurora. This is one of those ones that Dennis Brzezinski managed to photograph from up in Tarbert Ness in the north of Scotland. Dennis often complains about the light pollution from his aurora. They kind of distract him from the most important thing he should be doing, which is actually imaging comets. And I know Dennis is watching at the moment. So, you know, all these pretty pictures of aurora, but he does get some wonderful aurora. I've been up there many times. I've never actually been lucky enough to see one from his observatory, but he certainly gets very nice views of the Northern Lights. Of course, you can only do that when the sky is reasonably dark, and we have our own huge natural source of light pollution, but which can also be a really interesting object to observe. But for various things that I'm going to talk about a little bit later, the Geminid meteor shower, for instance, the moon is a real problem. So just looking at the dates on here, we have new moon coming up on Boxing Day, 26th, and that actually corresponds to an annular eclipse of the sun. And we have full moon coming up on January the 10th, which corresponds to a penumbral eclipse of the moon. We also have the Geminids, great meteor shower, coming up on December the 14th, very close to the full moon in December, which is a bit of a pain for us meteor observers. But I'm always amazed by the kind of images that people can get. I get even more and more amazed by the images that Damien Peach can get, although he does have access here to a 1-meter telescope. So this is the Chilescope that he now uses. So his poor 14-inch Celestron obviously is not really cutting the mustard anymore, so he's using this 1-meter telescope. And basically this is now moving remote observing from deep skies to planet as well. So as I understand it, essentially there's a PC there in Chile that does all the video collection, and he does all of the processing locally in Chile on that machine using remote desktop, so that you don't have to bring the gigabytes of video back. But this is a really extraordinary picture, and it kind of, I remember when I was a lad, the kind of picture of the century was a picture taken by the Lunar Orbiter spacecraft, which was looking obliquely over Copernicus, and just the details you can see in these ramparts here is quite extraordinary, really amazing stuff. So yeah, this is the eclipse coming up on Boxing Day. Anyone going to see this one? I thought probably not. There are a few people who do actually travel even to see annular eclipses. So this is one of those eclipses where the moon is near apogee. And of course, at this time of the year, the sun, we're near perihelion. So the sun's almost as big as it can get, and the moon is quite small, so it doesn't fully cover the sun. So this is an annular eclipse. It starts at sunrise in Saudi Arabia, crosses the UAE and goes into Oman, and then heads out over the Indian Ocean here and eventually ends up in the Pacific. So there will be a few people who go to see this. Most of them will be situating themselves somewhere around Oman or around there to get the ring of fire at sunrise. There's also a lunar eclipse, a penumbral eclipse, nothing really exciting. The moon doesn't actually get into the Earth's umbra, but it does fit in the penumbra. This is visible from the UK on the date of full moon in January the 10th, in the evening, so about 7 p.m. If you go out and have a look at the full moon, it won't be quite as irritating as it normally is. It'll be a little bit fainter because it's in the penumbra. Of course, the big event that's happened recently is this. How many people saw the Mercury transit? A goodly number. That's not bad. Given how rubbish the weather was over the UK, I think people have been pretty lucky in managing to get cloud gaps and managing to pick up the transit. It's the last one, I think, till 2032. Is that right? I think when the next one is. So you know, we were lucky to actually get to see it, and we've had some really nice pictures submitted to the BAA. I haven't really got time to show all of them, but I just wanted to run through a few. This really nice sequence from Nick Quinn at Ingress, showing Mercury moving onto the disk of the sun. And you really realize when you see Mercury against the sun what a small planet it is. I mean, it was just over 10 arc seconds in diameter, moving on to the face of the sun. And of course, that's as large as Mercury pretty much ever gets, because we're seeing it in line with the sun there. Nice picture here from Richard Petrie a little bit later as it had moved onto the disk. On a wheeler, managed to get this with an aircraft flying across the sun and Mercury there. And that's a kind of really nice demonstration of the perils of imaging the sun in the southeast of England. Of course, if you use hydrogen alpha, you can get a little bit more detail. You can see granulation on the sun here. So this is a really nice image. And then this one, of course, on the cover of the current journal, Ella Bryant's picture showing a prominence and Mercury on the disk at the same time. So Imaging, lots of really nice images, not so many visual observations, but as you'd expect, Paul did this drawing from, I think with Pete Lawrence you were, weren't you? Yeah, well, that's possibly true, but you actually managed to get, did you actually see ingress, or did you see?
Yeah, that was really pretty.
That was your first view.
Try and get it into a little layer.
Yeah.
The clouds didn't clear in time, so.
Right.
But that's about the closest I got.
Very nice view, and good to have a visual representation of this transit. I thought I'd stick this one in on a claim that her plane was fully on the disk. My plane here is not quite fully on the disk, but I've used this in a couple of things I've done with schools to do some kind of physics lessons about the sun's 150 million kilometers away, Mercury about 100 million. And if you know the length of an MD-11, which us geeks know that is, you can work out how far the plane was away. It's about 35 kilometers away and about 30,000 feet. So there you go, bit of geometry there. And then Gary Gawthorpe sent this one through, and I thought, oh, he's got the image upside down, until I realized that actually this was taken in Florida. So in Florida, he could actually see the egress. So this is, I think, about the only image we have on our website which shows the egress. So Mercury went through its transit, and then it's done a brief display in the morning sky. So if you get up in the morning sky, you'd have seen, and you had a good eastern horizon, you'd have seen Mercury looping up. It moves so fast around the sun, it's gone now, but this is our current picture of the week on the BAA website. This is Leo Ertz's picture of Mercury. This is an image of an object that's just over 6 arc seconds in diameter. And I think it's just extraordinary that you can get that kind of resolution on an object of that diameter. I think it's one of the most amazing pictures of Mercury that I've seen, actually. If you wait a little while to the end of January, Mercury will do its little loop again, so you have an opportunity to see it in the evening sky. But the main thing in the evening sky that we're seeing at the moment, of course, is Venus. Venus coming up from the horizon, moving gradually north as Saturn is moving in the opposite direction. And they pass each other, I think December the 10th, 11th is the closest. If you look on the BAA website, that's one of our observing challenges at the moment. So if you do manage to get some nice images of Venus and Saturn passing each other, please send them in, put them on the members' pages of the BAA. It's a good way of displaying what you're doing and also sharing your work with other people. A time-lapse would be quite good to do as well, but of course that would need you to have clear skies every evening for the next 2 weeks. I think that's probably fairly unlikely. Saturn, of course, is now moving towards conjunction. Again, this is an amazing image that Damien sent in, taken with that 1 meter chilescope, which shows extraordinary detail again. But Trevor Barry's image is not bad as well. I mean, that's really good. But we've pretty much lost Saturn now as it moves in towards conjunction, the same with Jupiter. So really it's Venus coming up over the next few weeks that it'll be a good planet to observe in the evening sky. And we've had some pretty good pictures sent in, this one from Peter Meadows, and this one from Tim Hames. When I first looked at it, I thought it was buffalo. But there's not many of those roaming free in Oxfordshire. They're actually sheep. But you could believe they were possibly buffalo. There are 2 planets that are fairly well visible actually in the sky in the early to late evening. That's Uranus and Neptune. And this is a rather nice image of Uranus taken by Chris. What would be, it's about 3.5 arc seconds, I think, something like that, Uranus. So again, amazing that you can actually get such imagery with amateur telescopes. Now, there has been a little thing with Neptune recently, and I do apologize to the professional astronomers who are in the audience, but there is a website called the Transient Name Server. And this is a website that professionals use to announce discoveries, supernovae, nova, that kind of thing. And there's a professional survey called Master, which announced the discovery of an 8th magnitude transient object in Aquarius. And this being professionals, it wasn't just one person, it's basically half a university who appear as the author list. Now, you'd have thought that one of this huge and this no doubt very esteemed group of people might have checked what this 8th magnitude object in Aquarius was. Anyone want to have a guess? Neptune. So Robin very politely posted on the TNS, Neptune, question mark. And of course it was. So there you go. As far as I know, the master team haven't posted any follow-ups or no apologies or anything. You may remember that a couple of years ago there was an event where a guy in South Africa, I can't remember his name off the top of my head, discovered Mars in the Lagoon Nebula or something, wasn't it? As a bright transient there. So, you know, at least he was quite good about it. He got a certificate, actually. Anyway. Well, indeed, yes. So there you go. At least as amateurs, we're allowed actually to post. They trust us as amateurs, if you're registered, to post to the TNS. We're not allowed to post to the Astronomer's Telegram as amateurs, as I understand it, because we're obviously not, you know, trustworthy enough. And that's where the discovery of Mars was announced. Anyway, Terry Evans' picture there of Neptune, Triton, and Phi Aquarii. So if you do discover anything bright in Aquarius, do just check it's not a planet. Urban Leberia probably got there before you did. Anyway, in terms of discoveries, you may not be aware of this because it hasn't been that well publicized so far, but the BAA has started up a new system to distribute alerts to people. We used to have an email system, but for technical reasons, that was withdrawn. We now have a system called BAA Alerts. You can go to the website, you can sign up for that. There hasn't been much traffic yet, but the idea is that section directors can use it to announce anything that might happen to be coming up in the sky as an alert system. So I recommend you go along and register for that. Right, in terms of things near the Earth, the ISS is up there at the moment. We've got some good passes of the ISS. This is a really good one, which happened about an hour ago. But there's good passes tomorrow as well. And of course, yesterday, our friend Elon Musk, or a few days ago, launched SpaceX CRS-19, which is going up to rendezvous with the ISS. If it had been clear tonight, you may have been able to see both of them go over together. By tomorrow night, they should have actually docked. But if you can take images like this, and these amazing images by Chris Hooker, taken with a telescope and a high-speed camera, show amazing detail on the space station as it comes over. And you might think that that's you need really advanced equipment to do that. But there are these images, these are, I think, from a couple of years ago, but these are from Tim Burgess. And what these are is he had an 8-inch Celestron with a Canon camera operating in video mode on the back, and he just manually tried to follow the space station. And every now and again managed to get some good video of it. And it's amazing what you can see, even with that kind of very simple approach. Right, so the next bit is where I've got to be a bit careful about what I say about Mr. Musk and his associates. You will recognize, I think, these objects. These are the first launch of 60 Starlink satellites. They were sent up in May. This is just after they've been released, about a day after they've been released by the rocket. So the rocket they're launched on, Falcon 9, has a payload capacity of about 24 tons, which means it can launch 60 of these 380 kilos satellites up into space. So SpaceX plans are that these will be used to provide internet connections around the world. The first plans are basically to fill up low Earth orbit with about 4,800 of these things, and then move into higher shells as well. That's going to involve a lot of Falcon 9 launches, and it's going to involve a lot of these spacecraft being up in orbit. And as amateur astronomers, one of the things we worry about is what that's going to do to the night sky. Now, it is true that these things are only a problem when they're actually visible in twilight, but the trouble for us at our latitudes is twilight lasts most of the night through the summer, so we'll be seeing them a lot. This is Sierra Tololo. This is then visible in the night sky there. Not that long ago, a couple of weeks ago, the second batch went up. So bear in mind, there's only 2 batches now. This is the Falcon 9 launch a couple of weeks ago. This is another 60 of those satellites going up. There's going to be another 160 odd launches, something like that, of this to fill up LEO with it. And these are all the spacecraft. So each of these is about 350 kilos. They get pushed off, and then they spread out in orbit. They have ion thrusters that allow them to raise their orbits to their operational altitude. And we're already seeing the results of these in a lot of astronomical images. This is what our Meteor cameras saw a few days ago. This is William Stewart's camera at Ravensmoor. This is Clanfield, so you can see them moving there. The next one will be my camera in Chelmsford. You can see them moving up here. And then Alex Pratt's camera, which you'll see in a sec, you can see them moving across the sky. So these objects are going to become more and more of a problem. And I think as astronomers, there's probably not a lot we can do about it. It seems to be pretty much a free-for-all as to what people can launch. The practicalities of making these things darker is very difficult given the thermal requirements that the spacecraft has. So I think from an imaging point of view, we're going to have to just rely on more and more clever software that can somehow detect and remove these from our images. But it's not just visual stuff, radio as well. This is Meteor radio detection using graphs. This is William Stewart's detection of about 60 of these Starlink satellites as they went across. So I'm afraid they are going to become more and more of a problem, and we are going to have to somehow adapt to deal with them. Professional observers have got problems too, but in many cases they are closer to the equator, so they have less of a problem than we do far north. But unfortunately, having had to battle with terrestrial light pollution, I think we now have a situation where we're going to have to battle with these spacecraft as well. Another thing we have to battle with is the media. I get all of my astronomical news from the Daily Express, as I'm sure we all do. This is an example of actually relatively sane reporting. Talking about an asteroid pass, although it did say it was going to come dangerously close being 6 million kilometers. But David Swan got a really nice time sequence of it. How good are you as observers? Could anyone spot the asteroid on this sequence? I'll give a raffle prize to anyone, or one of the old raffle. See, I can't even find it now. Oh. There it is. Yeah, okay. So as an example, though, of how things in the media have just reached a state where you can't believe anything you read in the media. One of the things as an engineer I find incredibly annoying is that as engineers and scientists, we've spent hundreds of years trying to come up with an internally self-consistent of units for measuring distance, velocity, volume, whatever, which the media can't use. Everything has to be in the size of double-decker buses, but this goes to an extraordinary thing. It says, this is talking about an asteroid, it says, even at the lower end of the estimate, the space rock is believed to be 9 times as long as a queen-size bed and about 3 times taller than an average giraffe. So, I'm not sure that helps, really. I mean, I know vaguely what a queen-size bed is, but there aren't many giraffes that roam the streets of Chelmsford. So thank you, Daily Express, for that. Now come on to something much more serious, variable stars. Woo, cheers from the audience. So there are really two nice binocular variable stars that are worth having a look at over the next month or so. This one, Chi Cygni, which is very well placed in the evening sky in Cygnus at the moment, and it's coming up to its maximum. So it'll probably reach about 5th magnitude, something like that at maximum, Gary, that kind of thing. and that's due in January. So that's a star that's definitely worth having a look at, making some estimates of with binoculars. And there's another one which we all know very well, our Corona Borealis, which is a little bit more, needs a bit more effort at this time of year because it's a morning object. So it needs you to get up fairly early in the morning. And here it is, it's just recovering from its fade, but it's still reasonably active. If you look south at this time of the year, of course, we see all the winter constellations, Orion, Gemini, lots and lots of interesting deep sky objects in this region. And then sort of above us as well, we've got Cepheus. And not only do we have variable stars, but we have variable nebulae. And I'm just going to mention a couple here that are worth looking at. This one, Gabaldaghian's Nebula, which is illuminated by the variable star PV Cephei, is currently looking rather sorry for itself, rather faint, but definitely worth keeping an eye on. And then the other one, McNeil's Nebula, which is in Orion, just south of M78, has pretty much disappeared altogether. So again, another variable nebula to keep an eye on to see when it might come back. And of course, there are some really lovely deep sky objects in the winter. This picture of Rosette Nebula, I think, is particularly wonderful because it was taken from Stanmore in Middlesex. And it shows that with the kind of even with the kind of light pollution that we have to deal with, if you have the right techniques and the right filtering and the right equipment, you can get amazing pictures. But this picture of Graham Winstanley's as well just shows an amazing amount of the outer detail of an object that we all think we know very well, M42, but which every year I still have a go at imaging, because every time I look at M42 with maybe a new piece of equipment, I see something new. Meteors, we've got the Geminids coming up on the 13th, 14th of December. They've already started, but the peak's around the 13th, 14th of December. Unfortunately, they are at their peak pretty much at the time of full moon, so there will be a problem this year. But this bit of video here is a Geminid from a couple of years ago, taken with my Sony Alpha 7 camera and a nice fast lens. And there are now so many different video systems looking at the skies for meteors that we're collecting a huge amount of data on meteor showers. But even if you just want to do visual observing, that's still important to do. In the case of the Geminids, you'll just have to make sure that you try and get the moon out of your field of view behind something. It'll be quite high up, unfortunately. In fact, on maximum night, it's in Gemini. So it's about as bad as it possibly can be. The alternative is the Quadrantids, which are around in early January. Moon's conditions much better for those. The Quadrantids have a very narrow peak, but if you do get clear skies on January the 4th, and that's at least long enough after New Year's Eve that you should have recovered by then, get out there and have a look at the meteors. So then, sort of coming to the end, I haven't mentioned comets yet, and that's because, unfortunately, as Comet Section Director, I haven't actually managed to serve up any really bright comets. Unfortunately, no comets like these two. These are, we've recently started putting archival images in our Comet Section archive. So these are scans of material from a long time ago. The one on the left there is the famous comet from 1957, Comet Arend-Roland. And the one on the right is Comet Vest from 1976. So sadly, we don't have any comets quite like that. The brightest comet that we do have around at the moment is a comet that was discovered by Pan-STARRS in 2017. And it was a long, long way out when it was discovered, and it was about 20th magnitude. And it's been brightening slowly. It's coming into perihelion next year in May. But it has a big advantage for us that it's circumpolar at the moment. And it's actually passing through a number of constellations we're very familiar with. So it's currently in Perseus. It'll head through Cassiopeia. It heads very close to the double cluster, which you can just see sort of north of Perseus there. So very close to the double cluster towards the end of January. So quite a nice potential photographic target. It's not hugely bright, but it's something you can pick up with relatively small instruments. It's probably about 9th or 10th magnitude at the moment visually. It'll probably peak maybe 8 or so visually. There's quite a discrepancy between what visual observers see and what imagers get. But it's got a nice tail. This is a movie I did of it a few days ago. And in fact, again, to see if there are any really good observers in here, there's an asteroid moving in this frame as well. Can anyone see it? Yeah, so there it is. So that's an asteroid that I think was about 15 million kilometers away or something at the time. But I'll just run quickly through a few pictures. This one from Peter Carson, I think must have been one of the last ones that Peter did before abandoning the observing site in Southend and moving to the south of Spain. It's passed some really nice deep sky objects. So this one from Martin Mobley here, as it was passing by, which open cluster was this? M36. Okay, I can do the comets, it's just these kind of weird stationary star patterns. Dennis Brzezinski, an image from up there. And then Steve Arnold has now started taking some really good images of comets. And Dave Eagle here, a colour image. So keep an eye on that comet through the winter. It'll be well placed for us all. It'll be brightening slowly, definitely something to have a go at. Finally, on the comet front, there's this one, which I wrote a short article for in the last journal. This is Comet Borisov. This was discovered by Gennady Borisov, this guy here, using I think a 0.3 meter very fast Hamiltonian telescope, so specially designed for comet discovery. It looked like a fairly boring comet when it was discovered, but when its orbit was computed, it's actually got an eccentricity of over 3, which means it's actually come in from outside of our solar system. So this is the second only confirmed interstellar visitor we had. We had Oumuamua a year or so ago, which was more asteroidal. This is definitely cometary. It's on an orbit which is diving down through our solar system. It's just about coming to perihelion now. It comes to perihelion in December, and it's reaching about 15th magnitude. It's in crater, though, at the moment, so you need a more southerly telescope to get some imaging of it. But really an amazing object in the fact that amateurs, we can get images of objects like that, you know, lumps of ice that have come from other solar systems. Thanks to Martin Mobley, this is an image from yesterday using the Eye telescope. So unfortunately, I can't promise you any bright comets. But if we did rely on the media to tell us about bright comets, this was another great one. This is the Daily Mirror, unparalleled in its science coverage. Huge comet will fly past Earth this week, and there's a chance you could see it. So this was a few months ago, and it's about a comet called 168P, Hergenrother. At the time that this article was written, the comet was about 20th magnitude. So just to wrap up, I thought I'd put up this rather nice Christmassy picture and ask if anyone could guess what this actually is. Sirius. It is Sirius. So this is a Gordon Mackey picture of Sirius taken with a lens that he just wobbled around. So while Sirius was sitting there twinkling and scintillating in the sky, you see all of the colors of Sirius. So I think this is really neat as a kind of just a clever thing to do with a camera system. So that's our Christmassy picture. So thank you very much. Happy Christmas to everyone. Safe trip home. Don't forget that comet, and don't forget all of the other things too. But Venus and Saturn conjunctions, and the Geminids too. So happy Christmas, everyone. See you next year.
If I can just hold attention, just a few thank yous before people leave. Again, IOP, Paul Hardacre is sitting just on our your left, my right. Catherine McKenzie, working with Hazel prior to setting up everything for us. Simon Clark, Red Hughes, and Ken Foskett, the AV and IT team. Ella McConnell, main point of contact for today. Fran, the catering team. Mark Kidger, Emma, who's sadly had to leave to catch sort of train, and of course Nick. Anne Davis and David Boyd and Peter for the BAA stand. The raffles were donated by Simon Bennett from Widescreen, Space Rocks and Crystal Nebula, and the BAA team for overseeing registration, doing the raffle and general help, and you, the audience, for coming along and so on. So, as Nick has already preempted me, wishing you a safe journey home and season greetings, and hope Santa brings you what you want down the chimney with his. Hope he doesn't break the CCD camera when he arrives. Thank you very much indeed.
Thanks, the members, how their badges back.